This is an essay by Noah Giff that first appeared in 2010, Writing Clean, Testable, High-Quality Code in Python. Introduction: Writing software is among the most complicated endeavors a human can undertake. Brian Kernigan, co-author of the AWK programming language and K&RC, summed up the true nature of software development in the book Software Tools when he stated, "Controlling complexity is the essence of software development. The harsh reality of real-world software development is that software is often created with intentional or unintentional complexity and a disregard for maintainability, testability, and quality. The end result of this unfortunate reality is software that can become increasingly difficult and expensive to maintain, and that fails sporadically and even spectacularly. The first step in the process of writing high-quality code is to re-examine the entire thought process of how an individual or team develops software. Often in failed or troubled software development projects, the software was developed in a reactionary stream of consciousness where the focus of the software development was on getting a problem solved in any manner possible. In a successful software project, the developer is thinking not only about how to solve the problem at hand, but additionally about the process involved in solving the problem. A successful software developer will devise a way to run the tests in an easily automated fashion so they can continuously prove the software works. They are aware of the dangers of needless complexity. They are humble in their approach, seek critical review, and expect refactoring at every step of the way. They continuously think about how they can ensure their software is testable, readable, and maintainable. Although Python, the language, and Python, the community, are heavily influenced by desire to write clean, maintainable code that works, it is still quite easy to do the exact opposite. In this article, we will tackle this problem head on and explore how to write clean, testable, high-quality code in Python, a clean code hypothetical problem. The best way to demonstrate this style of development is to solve a hypothetical problem. Let's suppose you are a back-end web developer at a company that allows users to generate reviews, and you need to come up with a way to show and highlight small snippets of those reviews. One way to approach the problem would be to write a large function that takes a snippet of text and query parameters and returns back a character-limited snippet with the query parameters highlighted. All of the logic needed to solve the problem would be included in the one mega function, and you would simply need to keep rerunning your script until you got the result you wanted. With a dynamic language like Python, Perl, or Ruby, it is easy to develop software by simply banging away at the problem, often interactively, until you get what seems to be the correct result and calling it a day. Unfortunately, this approach, while tempting, often leads to a false sense of accomplishment that is fraught with danger. Much of the danger lies in not designing a solution to be testable, and part lies in not properly controlling the complexity of the software written. How can you say this function even works? You can have faith that it works because it worked the last time you ran it during development, but are you sure it doesn't contain subtle errors of logic or syntax? What happens if you need to change the code? Would it still work? And how would you know it still worked? What if that code needed to be maintained by another developer and he needed to make changes to it? How would he know his changes didn't cause something subtle to break? How hard would it be for him to understand what the code does? The short answer is, if you don't have tests, you don't know if your software works. If you stack together enough guesses, you may eventually build something that appears to function, but that no human could ever say with certainty ever worked properly. This is a bad place to be, and I have both written this software and helped debug software written this way. Fortunately, this condition is easily avoidable. Writing tests before, such as the case of test-driven development, or while you write your logic, actually shapes the way code is written. It leads to modular, extensible code that is easy to test, understand, and maintain. It is immediately apparent to the experienced developer when software was developed with testing in mind and when it was not. The software itself looks dramatically different to the trained eye. Without simply taking my word for it or visually inspecting code, there are ways to measure scientifically the difference between these two different styles. The first way is to actually measure the lines of code that are tested. Nose is a popular extension of Python's unit test framework that includes an easy way to run automatically a batch of tests and plugins, such as code coverage. By measuring code coverage during development, it becomes quickly apparent that it is almost impossible to get 100% test coverage for code that is composed of large functions with highly nested logic that are built in an ad hoc manner. The second way to measure the difference is to use static analysis tools. There are several popular Python tools that measure various metrics for Python developers, ranging from general code quality to specific metrics like duplicate code or complexity. You can measure the cyclomatic complexity of your code with either Pygmy or Pymetrics. What is cyclomatic complexity? Cyclomatic complexity is a software metric developed by Thomas J. McCabe in 1976 to determine a program's complexity. The metric measures the number of linearly independent paths or branches through source code. According to McCabe, it is best to keep the complexity of a method below 10. This is important because research into human memory has determined that 7 plus or minus 2 is the magical number of items that a human can hold in short-term memory. If a developer is working on code that has 50 linearly independent paths, then they are roughly exceeding 5 times the capacity of short-term memory in keeping track of what is occurring in that method. Simpler methods that don't tax all of a human's short-term memory are easier to work with and have been proven to be less error-prone. A 2008 study by Energy found a strong correlation between cyclomatic complexity and faultiness. Classes that had a complexity of 11 had a probability of being fault-prone of 0.28, but rose to 0.98 with classes of a complexity of 74. Conclusion. In this article, we explored how merely thinking about testing influences the structure of software and how a lack of thought toward testing can prove fatally harmful to a project. We showed a complete code example that included both functional and unit tests and ran it against both code coverage analysis with Nose and two static analysis tools, Pylint and Pygmy. One thing we didn't have time to cover was how to automate this with some form of continuous integration testing. Fortunately, this is quite simple with the open source Java TM continuous integration system, Hudson. I would encourage you to consult the Hudson documentation and experiment with setting up an automated test for your project that runs all of your tests, including static code analysis. And finally, testing isn't a panacea, nor are static analysis tools. Software development is hard work. To get the chance even to be successful, we have to always be mindful of the real goal. It is not only to solve a problem, but also to create something we can prove works. If you agree with this premise, then this means that overly complex code, arrogance in design, and lack of respect for the power of Python directly interfere with this goal.